I will begin. Dear Heavenly Father, we thank you for this day. I again thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So I hope you watched the video on integration by parts. There will be more time for discussing that further, but at the moment I'm going to turn the page and start talking about integrals of trig functions. This is a necessary precursor to talking about implicit substitutions. Technically speaking, if your Calculus 1 instructor did a very good job, this should have already been covered, but invariably it slips through the cracks, all right? So first up, integral of cosine squared d theta. So what we're going to be looking at today, just to recap, is integrals of trigonometric functions, or powers of trigonometric functions, or their hyperbolic equivalent. And I'll be sharing with you a set of just common techniques that we can use to handle these. So at the end of this lecture, you should have a pretty good understanding how to integrate like powers of sine, powers of cosine, powers of tangent, powers of secant, and their hyperbolic analogs. All right? So one of the first problems people tend to get stumped on is integral of cosine squared. But I like what was done here. The first group of students said, oh, well, cosine squared, that's 1 plus cosine 2 theta over 2. Great. And then that breaks into these two integrals, which we can just integrate one at a time. And so there you go, theta over 2 plus a constant plus 1/4 sine 2 theta. Spot on. Perfect. Great. Here, I think you were hurt by the connection to previous lectures. You had it in your mind that this was an integration by parts problem. And once you go down that path, until you convince yourself that you're in the wrong part of town, people are going to keep stealing your stuff. So, sorry. But, I mean, it's hard to say anything can categorically not be done by integration by parts. Integration by parts is stupidly useful and has much wider applicability than you might realize. But this one, at this much I can say, that's the wrong way to do it. So there's a simple way to do this integral, which is to convert this to cosine squared theta times cosine theta d theta. Now that alone is that's not it. But if I do one more step, it becomes obvious how to do this integral. This is integral of 1 minus sine squared theta cosine theta d theta. Aha! See, now I can make a u substitution. U equals what? I want my du to be cosine theta d theta. So how about let's let u equal sine theta, yeah? That's pretty nice because then we've got integral of 1 minus u squared times du, which we can integrate to get u minus 1/3 u cubed plus a constant. And then going back to the thetas, that gives us sine theta minus 1/3 sine cubed theta plus a constant. If you really understand what I just did, you should be able to integrate any odd power of sine or cosine. The integral of any odd power of sine or cosine can be done by similar calculation. In fact, the same is true for cosh or sinh, right? For kicks, what if you were integrating sinh cubed? How would you do that? So what I would do is I'd say, well, that's sinh squared times sinh. And how can I convert sinh squared to cosh squared? Remember, cosh squared minus sinh squared is 1. So sinh squared is what? Yeah, cosh squared minus 1. And then we're off to the races, see, because we can make u equal to cosh. Cosh of theta is u. Du will be sinh theta d theta, and that's going to do it. So we got u squared minus 1 du, and I'll just go ahead and get straight to the answer. 1/3 cosh cubed theta minus cosh theta plus a constant. There you go. Enough of that for now. I'm gonna go on. So this one, so we did cosine squared. I did cosine cubed. Cosine to the 4th. You have started down the right path. And then that happened. All right. So this is in the right. You're in the hunt. You just got to think about it as 1/2 1 plus cosine 2 theta. 1/2 1 plus cosine 2 theta. All right. And then what do? Multiply, right? What do we got? 1/4 1 plus 2 cosine 2 theta plus cosine squared of 2 theta. Well, the first two terms there we can integrate, right? None of us should have to break a mental sweat to do that. What's the integral of the first two pieces? We got what? Theta over 4 plus 1/4 sine 2 theta. All right. Now that pesky cosine squared 2 theta term, what are we going to do there? Well, what we'll do is use the double angle formula again, or the half angle, whatever you label this thing. So this is, we can replace that with 1/2 of 1 plus the cosine of twice of 2 theta, which is otherwise known as 4 theta. So by trigonometry. Having made that replacement, we can integrate, right? That we can integrate. So answer. Theta over 4 plus 1/4 the sine of twice theta plus, well, I get a theta over 8 and then a plus 1/8 sine, oh wait a minute, 32nd sine of 4 theta plus a constant. Of course you can, what's a 4th plus an 8th? 3/8, right? So 3 theta over 8 plus 1/4 sine 2 theta plus 1/32 sine of 4 theta plus a constant. Now, if you understand what's happening here, what should you be able to do? Similar calculations, cover any even power of sine or cosine. Some of you would like me to put a word in here. The word is horrible, right? Even powers are harder to calculate, right? Because you have to nest these half-angle identities if we take this approach. There's another method for calculating powers of integrals of powers of trig functions, which is to use a recursion formula. One of those is derived in my integration by parts notes. I derived the recursion formula for the integral of sine, the nth power of sine theta d theta. That's an alternative route. If you memorize the recursion formula, you can bootstrap your way up from lower powers to higher powers, right? But I'm going to focus on things that require less memorization, perhaps, at the moment. Any questions so far? If I asked you to integrate sine to the fourth, what would you do? Split it. You get sine squared times sine squared, and then we got 1/2 of 1 minus cosine 2 theta times 1/2 of 1 minus cosine 2 theta. Multiply it through, you get a cosine squared 2 theta, and just very, very similar. What if we had integral of like cosine to the 6th theta? Then you multiply it out, and you take your cosine squareds and convert them back to 1/2 of 1 plus cosine twice the angle. It's the same thing again. There are alternate uglies, alternate ugly even problems. You could come to something like integral of sine squared theta times cosine squared theta, something like, well, that's not what I want. You could do something like sine squared theta oh goodness, I have no creative spark here at the moment. Well, I mean, it could be easier. Actually, let's do something easier. What if you had integral of cosine squared theta sine cubed theta d theta? What would you do there? Something like this. How would you deal with that? Okay, so you're telling me to change that sine squared to a 1 minus cosine squared theta and leave one of the sine thetas alone. That's what you said. I heard it. We all heard it. But that was the next step, right? He's like, pull off a sine squared with the intention of converting it to a cosine squared. You leave the one left over sine theta d theta to be the du. All right, so long story short, if there's a net odd number of sines and cosines, we can always kind of engage in this strategy to make a u equals cosine or u equals sine substitution. See, this means we can make this as the integral of u squared, 1 minus u squared minus du. See, if u is cosine theta, du is minus sine theta d theta. So that's why there's a minus there. Distribute the minus, what do you got? You could go either way.
Okay, I thought that's sine.
Well, I mean, sine theta d theta, I want to be the du. So that makes u equal to the cosine. You can try whatever u you want. The question is, when you actually make that substitution and plug it in, does it help you? We have to actually think through it, right? Don't try to memorize the step. You should try to understand the step. So minus minus gave me plus u squared, u to the fourth, and then the minus. Okay, anyway, so 1/5 u to the fifth minus 1/3 u cubed plus a constant, and then go back to the angle cosine theta. So that's 1/5 cosine to the fifth theta minus 1/3 cosine cubed theta plus a constant. As much as it pains me to waste precious lecture time on this. All right. I'm going to move on to integral of cos squared theta d theta. Now here, we have various options. This is not one of them. So, can you guys tell me, what is cos squared theta? Can you simplify it? Sinh, yeah, okay, but sinh we also don't know the integral of sinh squared. So you're right. Yes, it's sinh squared theta plus 1. Yeah, sure. Yep.
Well, there's like identities with
Identities with E. That's one path. Very good. And that's your path. We have actually worked out the other day. So the one that you guys are not giving me, and it's fine. But this is one thing you could do. This is an identity for hyperbolic cosine. Some of you were asking me why I was doing those things that day. This is one of those reasons. Because if you know that, then you can integrate it straight like this. Yay. Or we can do the exponential thing you guys were talking about. That's another path, which is a good path to know about. So let me do it two ways. Why the 2 in the middle? Oh, yeah. So this is method 1 up here. And I'm working on solution 2 down here. Very good question. Yeah. Obviously, solution 1 only works if you know what? So, some identities for the hyperbolic functions, right? If you don't know that identity, well, you can't do it, can you? The algebra I'm about to do is essentially the derivation of that identity, though. If you look at this and just regroup things, this is 1/2 of 1 plus, this, what's in the integrand is exactly this. But alternatively, of course, we can just use this to do the integral. Because you guys like to integrate exponentials, yeah? So we get 1/4, 1/2 e to the 2 theta plus 2 theta minus 1/2 e to the minus 2 theta plus a constant. You're like, well, that looks different than your first answer, but it's not. If you just take this, which I'll underline in blue, and regroup things a bit, what we're looking at is, what's 2 over 4? It's a half, so theta over 2. And then plus 1/4 of 1/2 e to the 2 theta minus e to the minus 2 theta. But what is that? What I put in the square brackets there in the blue, soon to be green, what is that? Notice the minus. That's sinh. That is sinh of 2 theta. So, same answer. Different method. Well, in some sense, you really should never be terrified by an integral of cosh or sinh or some power, because you could always just swap it out for a corresponding problem about exponentials, or you can just do algebra and do integrals of exponentials. But the trouble with doing that is sometimes you'll lose track of what the underlying hyperbolic function is you're looking at, and that could be a big disadvantage for a given problem. In some sense, it's much better to write the answer in terms of hyperbolic sinh here. as opposed to just exponentials. Anyway, that's how you do that. Any questions? All right. Tangent squared. Tangent squared. So I know time was short, but this is the wise path. Remember that secant squared theta is equal to 1 plus tangent squared theta, right? This identity we know for secant and tangent. It's the Pythagorean identity, which means that I can replace tangent squared with a 1 minus secant squared theta. Totally on board with that. And then these are, again, misdirection on my part. Sorry, last 2 hours about integration by parts. You know. So the way this works is if you guys come up and you participate and you try, I don't take off points, right? So it's no pressure, right? You just come up, you try your best, you see what you know, see what people in your group know. That's it, right? I mean, if you don't get the problem right, it's not like I'm like, oh, this person, that person, this person, they know what they're doing, haha. I won't give them an A. I mean, as if I'm that organized. Come on. All right, so your secret is safe with me in plain sight is what I'm trying to tell you. Anyway, so once we have that, we're done. See, because integral of 1 is theta, and integral of secant squared, there's no more thinking to do here. This is an elementary integral. Yes? What have I done? Oh, curses. Minus out here. Thank you. Fine, I'll not do that. Thank you for that. I'll do stupid stuff. I'd say on occasion, but the occasion when I do stupid stuff is class. So let's see here, secant squared. So you're like, you have no class. I was like, haha, see, we're safe. So tangent theta minus theta plus a constant and game over. That's it. Remember, secant squared is one of our elementary integrals because we know that the derivative of tangent is secant squared. So when you get to integral of secant squared, do you have to think about it? Well, if you do have to think about it, that means that there's like a major hole in your armor, right? You need to fill that hole because you shouldn't be spending time thinking, how do I integrate secant squared? You should just be like, integral of secant squared is tangent. Done. All right? We good? So it's kind of funny, but in some sense, the integral of cosine squared is much harder than the integral of tangent squared, isn't it? You know, just a shout out to last semester, integral of tangent theta d theta, we know how to do that one. What's that? That's an odd number of sines and cosines, right? So that's the sine theta d theta over cosine theta, which is the integral of, what, minus du over u, which is minus the natural log of the absolute value of u plus a constant, which is minus the natural log of the absolute value of cosine theta plus a constant. So just a reminder, we can integrate tangent theta on its lonesome by a u substitution, much as we were doing in the first about half dozen examples today. I'll put the gloves back on now. What if you had integral of tangent cubed? Oh, I don't know right offhand what to do with integral of tangent cubed, but we'd have to look at that one. Tangent to the fourth seems like it wouldn't be that bad. But anyway, here's a couple. Integral of secant. So this is the integral of the square root of tangent squared theta plus 1. True. True, but does this help? You're like, well, I know how to integrate the square root of an arbitrary thing, so this is helpful. Is not a true statement. So I don't disagree with what's written. I just don't think it helps. So, you know, when I think about how to do this, I think, oh, well, I'm going to let u equal to the secant theta plus the tangent theta. Let u equal to secant plus tangent. Now, admittedly, what? Why would you do that, right? Well, let's just chase this rabbit here for a second, see where it takes us. What's du? I'll do du d theta. It's secant theta, tangent theta, plus secant squared theta, right? You can factor secant theta out of that. What do we got? We got du d theta is secant theta times tangent theta plus secant theta, yeah? Notice that the thing in parentheses is exactly u again, right? So with a u equals secant plus tangent substitution, I find the following cute identity. I find that du over u is secant theta d theta. So you guys at this point have seen dozens, probably, of u substitutions in your calculus education, right? You've never seen one like this, right? This is out there. But look, the magic happened. So integral of secant theta d theta is du over u, and voila. Natural log of the absolute value of u plus a constant, which is natural log the absolute value of secant theta plus tangent theta plus a constant. And there you go. That's how we integrate secant theta. So in the context of a larger problem, all right, if the problem is not just the integral of secant theta, you're allowed to cite this result. All right, so if you were doing some other problem that took a half a dozen steps to get to this, and then you find yourself faced with integral of secant theta, you may say, as we know from class, the integral of secant theta is the log of the absolute value of secant plus tangent. But this is a non-obvious result. Weirdly enough, the integral of secant theta comes up in a lot of applications. Probably come up another half dozen times in this course in various problems and circumstances. There is another way to derive the integral of secant theta using partial fractions decomposition. Do we know that? No, so I had to show you this way at the moment, all right? Obviously, choosing u equals secant plus tangent is a dirty trick, right? But maybe if I do this and I ask you what's the integral of cosecant theta d theta, maybe you could come up with what you should do there. What's that? U equals what? I'm pretty sure u equals to what will work? Cosecant cotangent. Cosecant theta plus cotangent theta. Each one of those has a derivative which picks up a minus, right? The derivative of cosecant is minus cosecant cotangent. The derivative of cotangent is minus cosecant squared. So we should be able to go through a very similar calculational process to do that one. I won't work it out. Oh, I think this one, did I already do that one by accident over there? I did cosines, what did I do? Cosine squared. Oh, this is sine times cosine cubed. Oh, you guys were maybe, well, what we're going to do here is just do, this is the integral of u cubed times minus du for u equal to cosine. If u is cosine theta, du is minus sine theta d theta. So I've got the sine, I've got the d theta, right? I got to throw in a minus to be fair. And so the answer here is minus 1/4 u to the 4th plus a constant, which is minus 1/4 cosine to the 4th theta plus a constant. So I think, with what I've done so far, this gives you a pretty good cross-section of how we do integrals of powers of either sine, cosine, cosh, sinh, or secant, tangent, all right? There are similar things that could be said about like hyperbolic tangent or hyperbolic secant powers, all right? But you know, you gotta keep both eyes open, right? So you know, some calculus professor gives you a problem on a test, says like integral of e to the x cosh x dx. What should you do? Hey, didn't we integrate parts e to the x cosine x last time? Maybe we could integrate by parts two times and hope it loops, right? Should you take that bait? Or should you do something else? How would you calculate that integral while I'm erasing? Think about it. So, time's up. What do you think? Should I integrate by parts? No. What's that? You saw through my plot. Very good. So, I mean, this is in some sense a mathematical prank. So this is 1/2 integral of e to the 2x plus 1/2 integral of dx. So we got 1/4 e to the 2x plus x over 2 plus a constant. If hyperbolic functions were covered in your Calculus 1, this very well could have been a problem on your final. Yeah? Or how about this? Integral of cosh of the natural log of x dx. What would you do with this thing? That's too easy. Let's do tanh. This is really what? Integral of e to the log of x plus, or rather minus, e to the minus log of x divided by e to the log of x plus e to the minus log of x. Why do I do that? I mean, what am I doing? Remember that formula we wrote down for hyperbolic tangent of something? I'll use theta. It's sinh theta over cosh theta, right? But that's 1/2 e to the theta minus e to the minus theta over 1/2 e to the theta plus e to the minus theta, which of course gives me that pattern. The difference of the exponentials divided by the sum of the exponentials, the halves cancel. I'm putting theta equal to the natural log of x. Then we could simplify, right? What happens there? I'm not sure how you turn the projector on in here right now. Oh, there's a piece of paper that's covering up the thing. So it looked like there was nothing. If I just move the piece of paper, there's this thing. Mystery solved. All right, there we go. Look, so e to the log x is x. What is e to the minus log of x? That's equal to e to the log of x to the minus 1, which is what? X to the minus 1, also known as 1 over x. So we're looking at minus 1 over x upstairs plus 1 over x downstairs dx. Can you do that integral? I'm not sure we can at the moment. To clean that up, I would multiply by x over x. It would give me x squared minus 1 over x squared plus 1 dx. Okay, fine. I can actually do this one. Here's how I do this. This is a little bit off the beaten track for today's topic, okay? So my apologies, but what I do when I see something like this, it's quadratic over quadratic, right? So to simplify this, I try to make the numerator look like the denominator in a kind of sneaky way. So I replace this minus 1 with plus 1 minus 2. In so doing, I can then rewrite this as the integral of 1 minus 2 over x squared plus 1. Now it's an elementary integral. It's just x minus twice the inverse tangent of x plus a constant. Why did I ask this? I should have asked this. This makes a really kind of interesting test question, actually. But, oh well. I don't feel like I've ever done this integral before. I should have done it. It's fun. All right. A few other things in the section I should show you. All right. One thing I should do is integrate the nth power of sine of x dx. What would this be equal to? Come on. If we did this, we could do an integration by parts. So what's the integral of sine? Minus cosine, right? And that gives me n minus 1 sine to the n minus 2 power of x cosine of x dx. So you notice you got a cosine and a cosine here, right? So you trade that for 1 minus sine squared x. What happens when sine squared x hits sine to the n minus 1? So putting in that cosine identity, we get two pieces. We get an integral of sine to the n minus 2 power, all right? And also integral of, whoa, check that out, yeah? Wait a minute. This is what we started with, right? So that means you could solve this formula for the integral of sine to the nth power in terms of sine to the n minus second power. So if you know the integral of sine squared, you could use it to sort of bootstrap your way up to the integral of like sine to the fourth. Or if you know the sine cubed integral, you could use this formula to get your hands on integral of sine to the fifth, and so forth and so forth. All right, this is the recursive formula for sine. Actually, this is not the formula. I have the formula cleaned up in the notes. I'll show it to you here in just a second. I wanted to demystify where it comes from. That's just it. That calculation right there. Come on. You can do it. All right. Let's not look at my email. It's the worst thing, right? Like you open your computer and you got some private email and you got the video going. Instant editing. It's horrible. Yes?
If we were to get a problem on like a test that's in like that form, would you expect us to derive it that way, or if we memorize the formula?
If you memorize the recursion formula, you can use it. However, unless the problem says to calculate the integral of sine to the fifth power, do not use the recursion formula, for example. If those instructions were explicitly stated, then I guess you'd be up a creek. Let's see here. Hey. Oh. HDMI, right? All right. If I can find a laser. So here, example 9.1.11 in the integration by parts was this. This is the rest of it. Integral of the kth power of sine is given by the integral of the k minus 2th power, like that. And I actually use that to calculate the integral of the 4th power of sine here, right? And you can contrast that to what's the integral of sine to the 4th look like in my notes. Like if you go ahead a bit, in section 9.2, I calculate the integral of sine to the 4th using the method I talked to you guys about today, right? To replace sine 4th with sine squared squared, and replace that with the half angle identity, square it, integrate term by term, you get this. And it is a little bit disconcerting. Like this answer looks very different than the one that's given to you by the recursive formula. By the way, if you're looking at this in the proper PDF reader, you can actually click on that. It will take you back to the previous section. Yeah? So you can compare this answer. I mean, the 3x over 8, that looks the same, but the rest of it looks kind of different, right? But there's interesting trigonometric identities which allow you to get from one to the other. The thing I haven't talked about today yet, and I probably won't talk much about, I'll just let you look at the homework. We talked about this a little bit before. Well, one thing is integral of secant cubed. Secant cubed is horrible. Well, it requires actual thinking. Almost anything, I can ask my wife how to integrate, and when we're walking, she'll just rattle it off. I said, what's the integral of secant cubed? It took her like a full 5 minutes of walking to work this out. That means it's hard. So these are adding angles formulas for sine and cosine. These are the product formulas for cosine. There's the product formulas for sine. We've derived these with the imaginary exponential before. But here they are all stated in the notes, and they allow you to do integrals like cosine times sine to the 5th, things like this. Now, these almost never come up past this point in the course, but you do need to know them for the next test. And they are important to like the study of wave motion and other things, beats on a string. Like the musical phenomena of beats has to do with the trigonometry here. And that brings us to section 9.3, which is unimplicit substitutions. With that, I will shut up. So thanks, guys. There should be time for questions about homework tomorrow. All right.